I need Nicaragua's essence in your life. Silence. It's a special brand. I require a milky Christmas. The base is fun, but I must have full aerial finger. Or arboreal. Milm. One of you guys can pick it up if you guys want to do that. My entire build just need to be flying in the air combat mechanics. You can make it again, but I will. See, I want either unparalleled aerial or unparalleled arboreal.
All right, so we got about a minute to get started here. Discord on leave notification doper.
No one is going to ask what arboreal means.
What do you mean, Daniel?
What's an actual word?
Oh, just a whole bunch of people coming in. You can turn that off, right? I mean, you know how to do that. You can go to, I cannot remember where in the settings, but you can turn off certain kinds of notification, like people joining and leaving and so on. Alrighty. So we got 30 seconds to go. The first thing I'll do is I will do the homework assignment for the carry look ahead adder part 2. So that's going to be the first thing we do, and then the second thing is the continuation of talking about signed number representation. Thank you, Aiden. So that would be the settings of you individual. So that's going to be on the right hand side of your name at the bottom of the overall left hand side of the screen. You click on that gearbox and then go to notifications, and then under that there's a whole bunch of switches about sounds, and you can turn off most of them. I only have messages still turn on because that's going to be it's important that I know somebody is sending a message, but I turn off everything else. But it's up to you. I mean, this is an individual setting. It is not a server setting. All right, it is time to get started. We are already 40 seconds past the time to get started. So I will work on the carry look ahead adder part 2. And I got 2 ways to get this started. I can use a preview, which means that you'll be looking at about the same thing that you guys would be working on. Alrighty. Alright, so question number 1 says in case you haven't finished the circuits K2 and K3 from the previous lab, now is a good time to finish those, and so on. So this project is more about the integration of the K1, K2, K3 subcircuits into the main circuit in order to finish the actual adder. Okay. All right. So the first thing I need to do is to find out whether I saved the file that I have worked on previously. So let me start up Logisim first. There we go. All right. So within Logisim, we will go to recent files, and yes, good thing I actually saved the file, because very often I do not save my own files, because it's not that important to me. All right. So now that we have this file, we can see that okay, I only got K1 and K3, so K2 is still missing. So let's go ahead and work on K2 first. Okay, so we go to project, add a circuit, K2. So now we have a new circuit K2, but we already know K2 and K3 they will share some similarities, at least in terms of the input pin and the output pin and the location of the pins. So I'm just gonna do a copy and paste into K2. and then we can go ahead and change only the parts that we need to change. Now, where do we get the formula for K2? Well, this is something that we have talked about quite a few times. So let me open a new tab to go back to the modules, and it will be under binary addition. So binary addition is right here. And we should kind of know where to find that stuff already. It is in section 6. So in section 6, we just look for the solved equation of K2, which is this one. So K2 is G1 plus P1 G1 plus P1 P0 K0. Okay, so we'll go ahead and duplicate this equation into Logisim. So here's Logisim, and I'm going to put it on the side just a little bit so you won't see what I'm working on. I'm just changing the text label, so this way I can put in the equation, so this way I don't have to go back and forth all the time. So K2 is G1 or P1 G0 or P1 P0 K0. All right, so now that I got it copied, we can go back to Logisim and to work on it. All right, so we know that we don't need all the AND gates. We still need the 3-input AND gate. We don't need the 4-input AND gate. So we'll go ahead and do some editing here. Okay, get rid of this guy, which also means the OR gate at the output doesn't need to be a 4-input OR gate anymore. So we'll go ahead and change this to a 3-input OR gate, like so. And then the output pin is also needs to be renamed to K2. There we go. All right, so we'll start with G0 this time, okay, because G0 is the one that is by itself. I probably want to remove all of these wiring. Okay, so let's go ahead and remove all of these wiring. And the way to do it is to select a whole area. And it basically just I'm just deleting a whole bunch of stuff that I don't need anymore. The splitter I probably still want to keep around, and the wirings are the ones that we don't need. If the selection area is only overlapping but not including a particular structure, that structure will not be selected in the process. So this allows for fairly aggressive selecting to really just kind of find the things that we need to delete, to get rid of. All right, so now we can finally get this thing started. We'll duplicate the splitter, so Control D, duplicate, and then move it up here. All right, so the equation says G0 goes straight to the OR gate. So G0 is, oh, excuse me, I take it back, it's G1. So this is G1, and we want to take that directly to one of the inputs of the OR gate. So I'm gonna do this probably in a very ugly way. Let's try to make this not so ugly. Okay. All right, so we get this one straight to here. The next one is the conjunction of P1 G0. So P1 is this wire, and it's going into a 2-input OR gate. So we got G0 up here. I guess it's better to flip the 2 AND gates around, just so that it would look a little bit better. Okay. All right, so this wire, which is P1, goes to one input of the AND gate, and then G0, which is this wire, would go to the other input. Cool. And then the last AND gate, or the second AND gate, the one that has 3 inputs, would take care of P1, P0, and K0. So we have P1, okay, which is, we can tap this one here. It has P0, and this is one that has not been used before, so we'll bring it up here. And also K0. Oops, that doesn't look good. Okay, it would work, it would have worked, but it just doesn't look good. So now we have K0 going into the last input of the AND gate that has 3 inputs. So now we take the output of the AND gates to the input of the OR gate, like so, like so, like so, and now we are done. Okay, we have K2 now. Now I'm just scanning the text area just to make sure that I don't have any questions at this point. So it seems like we don't have any questions. So some people may say, then what about P2 and what about G2? Well, those are really not used. So as long as these wires are just kind of dangling and not going anywhere, it is perfectly okay for a splitter to have a split end that doesn't connect to anything else. Okay, that's perfectly okay. It just looks kind of awkward. Okay, so now we go to the appearance. There we go. And between the appearance and the actual circuit, it is important to make sure that the ordering is observed. So we got P, G, K0, and then K2 on the other side in that particular order. So when I document the pins, I would also follow the same order. P, G, K0, and then the K2, and just move things into their correct positions. Right. There's one. Here's the other one. Look at that. And this is the last one. So now we got the appearance done, and now we can go back to main. There we go. So in main, in order to make things look nicer, I can move. Okay, I can move this one down a little bit, and unfortunately the wires don't move like that, so it just looks kind of ugly. Okay, now it looks better. Now we get a K2 component and put it. Okay, it's off by one little square. Okay, move this back up. Nope, it doesn't work. I suppose I can move it down by one more, and that doesn't work either because when I move, it also moves the wire. Okay, so we'll just kind of settle for the uneven spacing between K1, K2, and K2, K3. Okay, it just doesn't look very good, but it is still correct. All right, so we just hook up the wires like this. You can see how this particular way of doing things is easy when we need to work on the main circuitry, because P is a multi-drop signal where it connects to the P pin or the P port of K1, K2, and K3. Same thing for G and same thing for K0. So from the main circuit's perspective, it's very easy to wire up to the individual K circuits. So what is coming out of here is K1, this is K2, and this is K3. So now we need to start to think about what the sum bit is going to look like. It is an output pin. So here's the sum bit output pin. We'll label it as S for sum. And it's going to be a 3-bit output, because the width of the sum has to be the same as the inputs, which in this case would be X and Y. They're all 3-bit pins. And then we have one output pin that is the overall carry. So the overall carry, we can call it K3, we can call it K out, okay? But it's just the overall carry. So now the question is, how do we get the sum bits? The sum bits is the exclusive OR between the K and the Q bits. Q bits is easy, okay? We got it here. The K bits, on the other hand, is in tiny little pieces, because we got K0, we got K1, we got K2, and we got K3. So the most common mistake is to look at K1, K2, and K3 and have those merged into a single K wire, and then we get to the exclusive OR gate. So let's make an exclusive OR gate first, okay? Because we need the exclusive OR to compute the sum bit out of the Q and the K bits. Restrict the input to 2 ports, change the data bits to 3, because this is the whole point of having a multi-bit gate, is so that we don't have to have one gate per bit, okay? And this is coming from a discussion from one of the labs I think is called a multi-bit lab. All right, so the input ports of this exclusive OR gate, they're all 3-bit wide, okay, which means wiring up K1 to this particular pin is not going to work because it's the wrong width. So we need a merger, which is the reverse of a splitter. So we go to wiring, pick up one of these splitters, and it's down. Oh, the top one. Okay, so we have a splitter. Make sure the splitter has a width of 3, and we will need all 3 ends of the splitter. Except this time the role of the splitter is a merger, so we want to flip the direction, flip the heading or facing. So this way the split end is pointing to the west. And now we can see that the merged end is going into one input port of the exclusive OR, and then the other one is just Q. So we'll just kind of tap it here. It's quite convenient. There's no need to use another tunnel. All right, so now the question is, we got 1, 2, 3, and 4 things to connect 4 things to. The 4 things that we need to connect from would be this, K0, K1, K2, and K3. So I don't know how many people make this mistake in this class, but K0 needs to hook up to bit 0 of the merger. K1 goes to bit 1 of the merger, and then K2 goes to bit 2 of the merger. There we go. And K3 is going straight to its own output pin, which is also labeled K3, but it can also be labeled K out for carry out. Okay, so now the circuit is all done, but let's go back to the quiz. Okay, let's go back to the lab and see if there's a question related to this. All right, so where is the lab? Okay. I might have lost it. Okay, that's fine. I'll go find it again. So we just go to this lab and go back to preview. And I think we're done with question 1. Okay, question 1 asks how many AND gates are needed in the K3 circuit. So if we go to the K3 circuit, am I in the right lab? Yep. Yep, this is part 2. So we go to K3, and it has 3 AND gates. So we go back here, we click on 3, and then we go to question number 2. So question number 2 really only has one question, which is down here. It is basically asking us to set up X, Y as input pins as well as K0, and then we want to go to a particular place to poke the wire to find out what it is reporting. So in this particular case, because it depends, if you reattempt the quiz or the lab, it's likely to give you a different value to begin with. So we got 0, 1, 0 and 0, 0, 1 for X and Y. So we have, okay, I have forgotten already. 0, oh, that's the wrong circuit. Go back to main. So we have 0, 1, 0. Okay, poke tool, 0, 1, 0, and then 0, 0, 1 as X and Y, and then K0 is known as a 1, like so. So let me just double check. 0, 1, 0 as X, 0, 0, 1 as Y, and K0 is a 1. Okay, that's exactly correct. And the question asks you to use the poke tool to poke the wire coming out of the merger of the K bits to the gate that computes the sum bits. Okay, so we are poking here, and in this case I only need the number to the right hand side of the slash, and this is the slash that we are talking about, and it's -1. So we go back to the quiz and answer -1 over here, and that's it. That would be the entire thing. and then we click submit quiz, and hopefully get all the points. Yep, so I'm getting 5 out of 5 points, and that would not be a bad thing. All right. So Antoine says, why is an exclusive OR gate used to sum versus a OR? Well, that depends on how the S bit is computed, and that is explained in the module. And let me go find the module. Okay, this one will do. So when you look at the S bits, okay, I can see if I can do a search here. So S bracket, nope, it doesn't do that. In that case, it's probably known as a S subscript something. So right there, okay, so look at this definition here. The sum bit is the R of Qi and Ki, and then R is exclusive OR. The fact that the Q is the exclusive OR between Q and K, that was, okay, I take it back. The fact that R is exclusive OR was already explained in the first part of this lab. Okay, so Dawood said, how do we distinguish between which gate we should use? Well, since R is exclusive OR, we choose exclusive OR. So I'm not sure whether Dawood is asking the question of how do we relate R to exclusive OR, which is documented in the module itself, or whether how do we find which of the gates is exclusive OR. Okay, Tom, are you clarifying Dawood's question? When both parts are equal, what does it mean by exclusive OR? Exclusive OR is exactly the same as how we define. Okay, so let me do this. Exclusive OR. So exclusive OR, the exclusive OR between X and Y is exactly how it is defined here. So I'm not quite sure what Tom is asking. Okay, so apparently I answered the question. But did I answer the question for Dawood? Because I wasn't quite sure what the question was asking, because there were two ways to interpret the question. All right. Since there's no follow-up from Dawood, I'm guessing that question is okay. Now I'm suspecting. Yeah, so Dawood is not using Discord to watch the lecture, and therefore we have a lag between the time when I ask and the time that he or she, I cannot know the gender, but there's a lag time. How do we know which gate should be used when we try to work on LogicSim? Well, now that you know that Q is exclusive OR, then you go to LogicSim and you look for exclusive OR in the gates. So here we have exclusive OR. That's kind of how we know it's exclusive OR. This has been talked about before, because I already explained that exclusive OR is known as EOR or XOR. Okay, so I'm guessing that issue is resolved. This means, it is important to kind of take notes also, because certain things I talked about in the lecture may or may not be in the in the modules. So it is also important to take notes when I'm talking, or when you watch the recorded version. So I have a recommendation. Instead of using YouTube to watch the live stream, try to use Discord to do it, because Discord has very little lag time, and as a result, I don't have to wait a very long time before I can confirm that there are no further questions. All right, so I think this pretty much answers the question for the homework assignment, unless somebody else has a question. I'm not seeing anything, so I am going to assume that there are no further questions. If you do have a further question, you can kind of put it into the text channel. I will go back and check it, once in a while. So assuming there are no questions about the lab, okay, so I do have one point to make. Okay, so from the questions that I have been getting, I think it's because there are pieces of information, at different places. So it is important to kind of track all of those pieces and try to associate those pieces, and see how they relate to each other. And that really is what studying is about for this class. There's nothing to memorize, okay? Because the exams are all open book and open notes, so you don't have to memorize anything, but you do have to make the association. Okay, so I am not sure what you can do to make all those associations, but that is what you need to do. All right. Okay, so let's go back and talk about signed numbers. Okay, so we go back to the main module, and then we head out to signed representation, which is here. So this is the module that we started last week, and I believe at the end of the lecture on last Thursday, I mentioned, please read this entire module and possibly the one after that over the long weekend, because I want people to be prepared for this topic. And if somebody is asking me, really, are you expecting me to really read this module before class? The answer is pretty simple. Yes, I do. If I did not expect it, I would not have said it. So there we go. So I'm assuming that you have read this module already, and now we are just going to kind of go through the module and try to understand how signed numbers work when they are represented as only zeros and ones. Okay. All right, so that we start with a discussion of arithmetic negation. In other words, we look at the negation of 45, which has the value of negative 45. So this operator by itself is the arithmetic negation operator. So now the question is, what do we know about arithmetic negation? We know that if you apply negation twice, you get a number back. So the arithmetic negation of the arithmetic negation of x is always just x, okay? X being an integer in this case. We also know that if you know how to take the arithmetic negation, you can kind of use that to do subtraction. But at the same time, we know that x plus the arithmetic negation of x is always going to be 0. X minus y is also known as x plus the arithmetic negation of y. So I'm bringing this up in section 3 because if we can find a magical operator that will give us the same properties, okay? It will give us the same property that it is its own inverse function. It will give us the property that it will find the inverse of a particular value. And it will give us the same property of you can use it to implement subtraction. Then whatever that magical operator is, we can use it as if it is really just arithmetic negation. And that is why that's the significance of section 3 is what qualifies as arithmetic negation. And then section 4, is really kind of nice if you can have a picture of a circle, and in the circle we basically label the slots from 0, and you go around the circle, and we label those as 0, 0, 0, 0, 0, 0, 0, 1, and then we keep going until we get to 1, 1, 1, 1. In which case the 1, 1, 1, 1 would be next to the 0, 0, 0, 0, except it's on the opposite side of 0, 0, 0, 1. All right, so is everybody getting that picture in your head? All right. So based on that picture, which I drew a smaller version of last time, which with only 3 bits and 8 different values. So from that picture, we kind of see that, if you start with 0 and you go to the negative side by 1 slot, which is the -1, we get the bit pattern of 15, or 1, 1, 1, 1. So as a result, okay, if you keep following this notation here, we eventually get to the labeling of the bits, the bit patterns, and we end up labeling 1101 as -3, and we end up labeling 1111 as -1. But we also know that 1111 can be interpreted as 15, because 1 plus 2 plus 4 plus 8 is in fact 15. So now the question is, which one is it? I addressed that question last Thursday as well. Does anyone remember my answer to that question? Should 1111 be a -1, or should it be 15? I believe that my answer should be fairly easy to remember. So I'm hoping you guys remember. Exactly. Okay. It's not don't care. Okay. I asked, the answer was, what do you care? That was my exact words. Okay. What do you care? Which is not quite the same as don't care. I'm actually responding to your question with a clarification of why do you need to know. Okay. So when I say, what do you care, it is not the same meaning as in normal conversation, where most people say, what do you care, meaning, I don't care. But in my case, when I say, what do you care, I literally meant, what do you care? Why is that important to you? Why is it important to you to know whether 1111 is representing 15, or is it representing -1? So I believe that was one of the things that we talked about last Thursday. I also answered the question myself, okay? Because I said, if what you are doing, or what you're planning to do with the bit pattern 1111 is simply adding, subtracting, then the answer is it's not important. You don't need to know, okay? On the other hand, if what you're trying to do is compare, then it is important to know. That was the discussion from last Thursday, which is summarized in section 4.1. Okay, so section 4.1 says, if you're just adding or subtracting, it really doesn't matter. On the other hand, if you're trying to compare, then it matters. Okay. So that's why we normally do not need to know what 1111 is representing. It's only when we are comparing that bit pattern with something else and we want to know the ordering, then we need to know. So section 5 is taking us back to arithmetic negation. And what it is saying here is we are basically dealing with a modular math system. So it is basically saying, if this is the math here, okay, if you are to subtract x, okay, whatever the bit pattern of x is, from the bit pattern or the value represented by 1 followed by 4 zeros, then we can rewrite it as this. Okay, so just kind of bear with me and follow this particular line of reasoning. So if you have a binary number, which is 1, 0, 0, 0, 0 in base 2, and you want to subtract x from that particular bit pattern, we can easily rewrite it as 1, 1, 1, 1 in base 2 plus 0, 0, 0, 1 in base 2 minus x. Because if you add 0, 0, 0, 1 to 1, 1, 1, 1, you end up with 1 followed by 4 zeros. In other words, I am just simply rewriting this quantity using an addition in itself. Okay. Now, knowing this is addition, okay, the parentheses is not useful in this case, so I take out the parentheses. And once I take out the parentheses, I can perform the add 0, 0, 0, 1. I don't have to do it here, I can first subtract x from 1, 1, 1, 1, then I add back the 0, 0, 0, 1. And that has to do with the, I'm trying to think, is it associative or is it commutative? I believe this is associative, aspect of addition. So that's why we can reorder things. Does anyone have a question about how this particular expression is exactly the same or give us exactly the same value as this expression here? Because that really is algebra, which I kind of assume that people have already in this class. So okay, Daniel is typing something. Order does not matter. That is correct. Whether we subtract the x first or whether we add the 0, 0, 0, 1 first does not matter. Okay. So this is kind of, it's interesting because now we can say, oh, how do we perform this operation here? Now these are arithmetic operations. They are not bitwise operations. But when we subtract a bit pattern from 1, 1, 1, 1 as a base 2 number, instead of treating this as an arithmetic operation, we can actually treat this as a logical operation, a bitwise logical operation. So let me show you what I mean by that. Okay, so I'm going to open up a new page. And it doesn't open. Okay, I think that's because I have to close the other tab first from this morning. This is from the morning and it is still here. So I take that out. It doesn't want to do it that way. Fine. Yeah, somebody was mentioning processors in my other class, and that's why I was doing a little search over there. All right, so I would just go ahead and do it like this over here. So we have 1, 1, 1, 1, and I'm going to space them out a little bit further. So we got 1, 1, 1, 1, okay? And the quantity that I want to subtract from 1, 1, 1, 1, I'm not going to give you actual bits this time. I'll give you the bits of, we'll call this y3, y2, y1, and y0. And now I want you to give me the answer, okay? What would be the answer? Now, normally, if I give you a binary subtraction and I do not tell you about the actual bits of one of the numbers to be in the subtraction, it would be kind of impossible to know the answer, okay? But in this case, we actually can figure out the answer. In other words, I can look at this place here and go like, this has to be 1 minus y3. And this one here has to be 1 minus y2. This one here has to be 1 minus y1. And this one here has to be 1 minus y0. In other words, I don't have to worry about borrows at all. Can anyone tell me why I do not have to worry about borrows at all? There's no borrow of 1 in this entire subtraction. I do not have to worry about the t row of the entire calculation. But why is that the case? It has to do with the borrow function. Do you guys remember the borrow function? B of xy, how is that defined? All right, so as you guys are thinking about it, I'm going to check out several things on the side. All right, so I'm getting back to the class right now. Okay, so let me just kind of quote the borrow function. B of xy is known as not x and y. Okay, not x. This time I'll make it extra clear. It's not x and y. There we go. All right, so what is the big deal if it is not x and y? Well, if the borrow is not x and y, and we know x is a 1, okay? So what is that telling you? Because remember, this row here, that's x. So we know for every single bit position, x is a 1. Not 1 is a 0. So if you plug in not x is a 0, then we know there's no borrow of 1 whatsoever. So without any borrow, let me put it in another way. Without any borrows of 1, then we don't need the t row. The t row doesn't serve any purpose. But then the next question is, so what do we know about 1 minus y0, 1 minus y1, and 1 minus y2, and so on? Well, as it turns out, it is this is equivalent to the logical knot of y3. This is equivalent to the logical knot of y2. This is equivalent to the logical knot of y1. And this is equivalent to the logical knot of y0. And if somebody is asking me, how can you make this equate, how are they the same? 1 minus y2 or 1 minus y is the logical knot of y. How do we know? How do we prove this? Okay. This goes back to a technique that we talked about at the very, very early part of this class. We use a truth table, right? We use a table to prove it. So the way we do this is we make a table with only one single independent variable, which is y itself. And then we use another column to compute 1 minus y. And then we use another column to compute the logical knot of y. So we make a table out of this. And y can only be a 0 or 1. When y is 0, 1 minus 0 is 1. When y is 1, 1 minus 1 is a 0. But when we go to the logical knot column, we'll get exactly the same answer. Because when y is 0, which is false, not 0 is 1, which is true. And when y is a 1, then not y is a 0. So we can see how the two columns, okay, we can see how the two columns, 1 minus y and the logical knot of y, are giving us exactly the same result when y is either a 1 or 0. This is why we can basically look at 1, 1, 1, 1 in base 2 minus whatever bit pattern of y. We can look at this as, in the C notation, it is known as tilde y. Tilde is shift back quote, on your keyboard. Okay, it's a very small kind of twirly little sign. Okay, let me magnify it so you can see it better. There we go. That operator is actually defined in C and C++ as logical knot. Top left of the keyboard. Thank you. Okay. So is this part going okay? Do we have any questions about this part? Okay, no questions. Very good. All right. But wait, hold on a second here. Okay, hold on a second here. Let's redo the derivation. 1, 0, 0, 0 in base 2 minus y is 1, 1, 1, 1 in base 2 plus 0, 0, 0, 0, 0, 1 in base 2, and the whole thing minus y. And then this equals 2. No, tilde is not the same as exclamation point. I will illustrate that in just a little bit using GDB. So give me a moment when I finish this discussion here. So 1, 1, 1, 1 in base 2 minus y plus 0, 0, 0, 1 in base 2. And that is, in parentheses, 1, 1, 1, 1 in base 2 minus y close parenthesis plus 0, 0, 0, 1 in base 2. And with this new piece of information, 1, 1, 1, 1 in base 2 minus y is really the bitwise knot of y. Now we say, oh, okay, so this is just the bitwise knot of y plus 0, 0, 0, 1 in base 2. Okay, so this is the first thing that we want to kind of remember. And let me go back and answer Daniel's question, which is probably on the mind of quite a few people. except nobody wants to ask. Okay, so I'll go ahead and address that question using GDB. So let me get out of this editor. We'll get back in here a little bit later. So we go into GDB without any programs because I don't need any programs to do this. Okay. So what I'll do is I will try to confine to 8-bit numbers. Okay, so an 8-bit number is an unsigned char in C and C++. Okay, so what I want to do is to illustrate what is the exclamation point versus the tilde in the case of C and C++. Okay, so the first thing we do is look at a particular bit pattern and print okay, unsigned char, which is probably not needed in this case, so we'll put it here anyway. Let's see what value will be good. Maybe 78. Okay, so it says 78 is 78, and it turns out to be the ASCII code of uppercase N. Okay, so no big deal here. So now the question is, what does it look like as a base 2 number? So we say print /t. I think /t is to print something in base 2. I could be wrong, but we'll see. All right, so that turns out to be right. So 78 as a base 10 number is also known as 1001111 in base 2. So now we want to look at performing the exclamation point, which is known as logical NOT. Okay, so we say print /t exclamation point of unsigned char 78, and it says it's a 0. Well, that makes sense, okay, because in C and C++, 0 means false, and anything other than 0 is not false or true. Okay, so 78 as a value is non-zero, and therefore it is interpreted as true. So we are basically asking what is not true. Not true is false, and there's only one representation of false, which is 0. But now we ask the question again, but this time we apply the tilde operator. Okay, so we have a tilde operator here, and then when we press the enter key, okay, darn, it doesn't work. So we want to do the casting somewhere else. Okay, we need to do the casting before or as the last thing, because I don't want to look at all the zeros, all the ones. Okay, so we look at this, and we can see how this value in $2 relate to $5. $2 is basically the mirror image of $5, where all the ones becomes zeros and all the zeros become 1. You can see how in $2, which is 78 as a base 2 number, is 1001110. Okay, but because we are looking at an unsigned char, which is only 8-bit wide, so when we look at the flip side, in terms of bitwise NOT, we get 1, which is reversing a 0 that we don't see in this particular position, and then this 0 is the bitwise NOT of this 1 over here, and then we have 2 zeros, which become 2 1s, and then we have 3 1s here, which became 3 zeros over here, and then we have one last, the least significant 0 here, which becomes a 1 over here. So I hope that answers Daniel's question. So Antoine, it's not an inverse, it is known as bitwise NOT. That would be the technical name of it. You turn zeros, individual zeros into ones, and you turn individual ones into zeros. Yep, you're welcome. All right. Oh, let's ask the other question. What about 1111 minus 78? Would that be the same as this? Okay, because that's what I was claiming earlier, right? So let's do that. Okay, so we say print /t. This time we want to have 1111 as a base 2 number. There's a way to specify base 2. I think it's a 0t or 0b. I cannot remember which one. I think it's 0b as a prefix. Then we can enter a binary value using in GDB. 1 1 1 1 1 1 1 1. So let me see if that works. Yep, that works. So now we want to look at 1 1 1 1 1 1 1 1 minus 78. Now this is kind of a cool thing to do, because what happens here is I'm specifying one number as a base 2 number. Okay, this is a base 2 number. I'm specifying another number in the subtraction as a base 10 number. But the difference, whatever the result is going to be printed as a base 2 number because of the /t. So we print this out. We go like, hey, this looks familiar. $7 as a result is the same as $5 as a result. So we can actually visually see how 1111 minus 78 is really technically the same thing as the bitwise NOT of 78. So I hope this helps to illustrate the point that I was trying to make earlier. And the mechanism is really quite simple. Okay, so let me go back to the notes and kind of further explain what the mechanism is. So the mechanism is basically, because this is the row of Q's, right? This is the row of Q's, and we know how the row of Q is defined because Q of xy is known to be x exclusive or with y. We just touched on this earlier today, okay? So if we know that x is a 1 already, then 1 exclusive or with whatever is the bitwise NOT of that thing. Okay. Okay, let me say that one more time. Okay, 1 exclusive or with whatever, say y, is really the bitwise, is really the logical NOT of y. And you guys look at me and go like, we are not convinced. Fine. We use a truth table. Okay, here's y, here's 1 exclusive or with y, and here is the logical NOT of y. Y is Boolean, so it can only be a 0 or 1. When y is 0, 1 exclusive or with 0 is a 1, and the logical NOT of y is also a 1. When y is a 1, 1 exclusive or with 1 is a 0, but also the logical NOT of 1 is also a 0. So now we can see how the two columns are the same. The two columns we're comparing is 1 exclusive or y versus not y. So this is the other way to look at this, is how the subtraction works. All right, but so these are the itty-gritty detail. So let's go back to this thing here and say, but what does this have anything to do with arithmetic negation, right? Because arithmetic negation, okay, arithmetic negation is just doing this. But we are not doing this, right? We are doing 1 followed by 4 zeros minus x. So what is the big deal? Okay, so I want you guys to think about this a little bit, okay? Okay, let me just type the question so that you can see what question you need to think about. So we'll say, how does 1 0 0 0 0 in base 2 minus y the same as just 0, just the negation of y? Okay. If you have read the notes, you already know the answer, but you may need a little bit of time to recall that. All right. So what is the answer? How come it is the same? Remember the modulo math? Everything is mod something, because when you are only given 4 bits to represent everything, then every operation, there's an implicit mod 16 in every single calculation. Yes, so Antoine is actually correct. Okay, so this equals to 0 in 4-bit computations. Because everything is mod 16, so if everything is mod 16, then it doesn't matter whether you mod it first and then you perform the operation, or you perform the operation and then you mod. Okay, so that's why when we subtract y from 1 followed by 4 zeros, it's the same as subtracting y from just 0. So now we kind of understand what the whole thing is, because now we can say, oh, so that is really the same thing as, okay, you're using our earlier derivation, it's really this, but that turned out to be the same thing as just the negation, arithmetic negation of y. You look at this and go like, no, that cannot be right, okay? That simply cannot be right. Let's try this on a few things, okay? So let's try out what if y is 0, 0, 1, 1 in base 2, which represents 3, right? Okay, so let's try out this, okay? So we say, okay, 1 followed by 4, 0 in base 2 minus 0, 0, 1, 1 in base 2 is the bitwise knot of y, which is now 1, 1, 0, 0 in base 2 plus 0, 0, 0, 1 in base 2. And that is 1, 1, 0, 1 in base 2. That is not negative 3, or is it? What do you guys think? Where have we seen that negative 3 is 1, 1, 0, 1 in base 2? We just saw it earlier today. All right, so I'm going to disclose where we have seen it. So we'll go back to the module, assuming I can find it. All right, so somewhere in here is 1101, so we'll look for it. 1101, and it is supposed to have found it, but it's not highlighting it because it is actually not part of the text. So I'm just gonna have to try to find it manually. There we go. Okay, so this 1101 here is representing this negative 3. And also up here, when we try to label the bit patterns on this 16-bit wheel, 16 slot 4-bit wheel, we would have labeled the bit pattern of 1101 as representing negative 3. So we have seen this before. So that means, in my calculation here, this actually makes sense, okay? It actually makes sense. So if I claim that this operation, so let me go ahead and further define what is 2's complement. So I'm going to use C2, as the function name for 2's complement. So when you try to take the 2's complement of a particular bit pattern, let's say it's bit pattern X, okay? It is defined to be the bitwise knot of X plus 1. That's it. That is called 2's complement. The negation of a bit pattern plus 1. And I claim that 2's complement is really the same thing as the arithmetic negation operation. You go like this, go like, no, they don't even look the same. They don't even look close to each other. Okay, one is an arithmetic operation, the other one is a bitwise knot and then an arithmetic operation. Remember all the properties that we talked about a little bit earlier about arithmetic negation? Let's see if this works, right? So we'll use very specific bit patterns to test this out. So if C2 really is arithmetic negation, then C2 of X should be the same as X. Okay? All right. Well, okay, Daniel is believing it, okay? But in this class, in all of my classes, I don't want believers. I want people who are skeptical. I need skeptics who would be asking Tech, show me this, okay? I don't believe you. Now, don't universally try that attitude in every single class, but in my class, that is what I want, okay? I want you guys to be skeptics. But I want you to be skeptics after reading my notes. And reviewing, all the material from previous weeks. Blind faith is not going to work in my class. Nope, not in this class. All right, so we'll go ahead and try this out. Okay, we'll say, okay, let's look at the C2 of the C2 of 3. Okay, so we have 0, 0, 1, 1 as a base 2 number. So we're going to work on this step by step and see if we can get this done. Okay, so this is the C2. Okay, we'll work on the inner C2 first. Okay, so the inner C2 basically boils down to the bitwise NOT, which is the tilde symbol of 0, 0, 1, 1 in base 2 plus 1. Okay, and that turns out to be 1, 1, 0, 0 in base 2 plus 1. And that one turns out to be 1, 1, 0, 1 in base 2. Yeah, we got that. Okay, we worked on this just before we get into this topic here. All right, so now we apply C2 to 1, 1, 0, 1 as a binary number. Okay, so now we take the bitwise NOT of 1, 1, 0, 1 in base 2 and then add 1 to the result of bitwise NOT. The bitwise NOT will give us 0, 0, 1, 0 in base 2, and then we add 1 to it, and guess what? Magically, it gets us back to 0, 0, 1, 1 in base 2. Wow, okay. Let's check some other things, okay? So let's check out the other thing, which is x plus the arithmetic negation of x is 0, okay? So if C2 really is arithmetic negation, then this also applies. So we want to look at the bit pattern of 0, 0, 1, 1 again. So we say, let's look at this 0, 0, 1, 1 in base 2 plus the 2's complement of 0, 0, 1, 1 in base 2. What is that? Okay, so we know 0, 0, 1, 1 is just that, but we also know that 2's complement of 0, 0, 1, 1 is 1, 1, 0, 1 in base 2. That has been shown quite a few times already up to this point. So we perform the addition down here. We'll use the long form of the addition, 0, 0, 1, 1 plus 1, 1, 0, 1. Okay, so now we have our Q row. We have our K this time because it's an addition. And then we have our sum down here. Yeah, this stuff really kind of relates to what we were doing in today's lab. Okay, just a little bit earlier. So now we look at 1 plus 1 is 0 with a carry. This is an implicitly 0 over here. 0 plus 0 is a 0. 1 plus 0 is a 1. Oops. 1 plus 1 is a 0 with a carry of 1. Oops. Ah. Okay. There we go. 0 plus 1 is a 1. 1 plus 1 is a 0 with a carry of 1. 0 plus 1 is a 1. 1 plus 1 is a 0 with an over or borrow of a 1. Okay. Oh, okay. So it does seem like 0, 0, 1, 1 in base 2 plus 0 plus 1, 1, 0 in base 2 does come out to be 0, 0, 0, 0. Ah, okay, that seems to work. And Aiden is asking, can we multiply -1 to x to get negative x? Yes, absolutely, in a math class. But to do that, you have to first represent -1. So, okay, so let me address Aiden's question. So if you were to carry out the multiplication of 1, 1, 1, 1 times 0, 0, 1, 1 in base 2, the question is, are we going to end up with 1, 1, 0, 1 in base 2? That is the question. So this is a tricky question, okay? Because multiplication requires bit shifting. And bit shifting is a tricky business because we need to extend the sign, at some point. And in this case, there's no need for sign extension, but in certain cases, we need sign extension. So the answer is yes. Okay, you can in fact get to 1101 by multiplication, but multiplication is an expensive operation compared to bitwise not and the +1. So that's why we don't use -1 times a bit pattern to get to the negated value. So is that kind of answering your question, Aiden? Yes, the answer is yes, you can do it that way, but because it's a very expensive operation compared to a bitwise not +1, so we don't do it that way. Okay. Yeah, we can definitely do it that way. It's just, in terms of how much silicon you're going to use to do that, it is quite expensive. All right. So let's see where we are now at. So we have just talked about 2's complement. And 2's complement is basically section 5 in the notes. So we are pretty much done with section 5 in the notes. Okay. And at this point, we have talked about signed value representation. But let's go ahead and apply that a few times, okay, just so that we know how this thing is applied. So we're going to stick with 4 bits for representation of the values that we're interested in. So we want to know how certain values are represented. Let's try to figure out what is -5, okay? So -5 in base 10 is what in base 2, okay? So the first thing we do is we say, we know how to deal with non-negative values, okay? So we first look at 5, and we say 5 is 4 plus 1, which is 100 in base 2 plus 001 in base 2. So if we are allocating 4 bits, okay, then we end up with 0101 in base 2. So now if we want to find the arithmetic negation of 5, okay, so -5 is the same thing as the negation of 5, which is the same thing as 2's complement of 5, which is the same thing as 2's complement of 0101 in base 2, and that becomes the bitwise not of 0101 in base 2 plus 1. That becomes 1010 in base 2 plus 1. That becomes 1011 in base 2. Done. So now we know that -5 has a 4-bit representation of 1011 in base 2. All right. There are a few things we can do, okay, other things we can do, such as if we are given 1100 in base 2, what is that really representing, okay, in base 10? In other words, if somebody tells me that 1100 in base 2 really is representing a signed value, okay, then what value is it representing? So how do we reverse the process, okay? So now we can say, first of all, because the most significant bit is a 1, we know it is representing a negative value. So knowing that it is it's representing a negative value, so we want to find out how negative it is. In other words, we're trying to find out the magnitude of the value. We already know it's a negative number. We just need to know how negative it is. So now we apply this theorem that we talked about a little bit earlier. The negation of a value is really just itself, so it should not bother us to perform this operation. Let me just kind of give you the full form of this derivation. Okay, oops. So does anyone have a question about this particular step? Double negation does not do a single thing. Okay, so if it doesn't do a single thing, then we should be okay with this, except the inner negation, I turn it into 2's complement, because we showed earlier that 2's complement is really doing the same thing as arithmetic negation. So now we have C2 of 1100 in base 2, and then we expand the 2's complement of 1100 in base 2, which is the bitwise not of 1100 in base 2 plus 1. And we look at the bitwise not is we flip all the zeros to 1 and all the 1s to zeros, so we end up with 0011 in base 2 plus 1. and then we end up with 0, 1, 1, excuse me, 0, 1, 0, 0 in base 2, and then we end up with -4, because 0, 1, 0, 0 in base 2 represents 4. So this way, we can be given a bit pattern, and we can find what value it is representing. And we can see this is all, how should I put it? It's all based on definitions, because the first thing is based on the identity of, it's based on the fact that negation is its own inverse function. The second one is based on the definition of C2. What we use C2 for is to perform the same thing as arithmetic negation. Going from here to here is based on the definition of C2 itself. It's 2's complement, which is 1's complement, otherwise known as bitwise NOT plus 1. And then from here to here, we perform the actual bitwise NOT. 1, 1, 0, 0 bitwise NOT is 0, 1, 0, 0, 1, 1. And then from here to here, we're just adding 1 to 0, 0, 1, 1. And then from here to here, we're just converting the base. 0, 1, 0, 0 in base 2 is 4. So do we have any questions up to this point? All right, so it looks like we are good so far. All right, so if this is good, then I have another way for you to look at signed representation. Okay, so let X be the binary bit pattern, and we'll say okay, binary bit pattern is totally redundant. Okay, so we'll say binary n bit pattern. Does everybody see how binary bit pattern is totally stupid? Yes, I'm calling myself stupid, but that's basically what it was. Does everybody see that? No? What? Okay. What is a bit? Okay, bit is the represent. How is bit defined in computer science? Yep, there we go. All right. So if bit is binary digit, then when I say binary bit pattern, I'm actually saying binary digit pattern. That's not a very intelligent thing to do. Okay. So, but when I say n bit, it's slightly different, because now I'm saying the width of the bit pattern is n. We only have n binary digits. Okay. Now, obviously, you can also say this is an n-bit pattern. Okay, fine. But the binary on the outside is an emphasis that we only got zeros and ones. Okay. So using this notation and also combining this with what we already learned in the past, x0 is bit 0 of x. So the most significant bit of x is n minus 1, because we count from 0. Okay, this is the most significant bit of x. Oh, by the way, this is where I can give you the key of today's road-taking activity. Okay, the road-taking word is MSB, and it has to be uppercase M, uppercase S, but lowercase b, because it stands for, guess what? Most significant bit. But some people may ask, then why do we use lowercase b? My English teacher says when you use an abbreviation, everything needs to be uppercase. But that's because in computer science, uppercase b is representing byte. To make sure that we understand this is most significant bit instead of most significant byte, we changed the case of the b to make sure it is lowercase. So it is just MSB. And somebody can make a new Gundam series and call it Mobile Suit Beta. Okay, we can use MSB for that too. All right. But I'm known to make mistakes, so let me just double check and make sure that really, in fact, is MSB. LSB is important too, the least significant bit. But the most significant bit is also known as the sign bit for a reason, and I will get to that in just a little bit, because I do want to make sure that I gave you guys the right information, because sometimes I remember things incorrectly, so I am just double checking. Oh, okay, thank you. You guys are fast. Okay, you got it done already. Very good. All right, so now that that part is out of the question, what is the value then? Okay, v is the value represented by x as a signed value. Okay, fine, poor English here. There we go. So v is the signed value represented by x. How do we express that? Okay, so we know the usual things. Okay, so we know v is 2 to the power of 0 times x0 plus, okay, I'm going to use this format here so I can use copy and paste at some point, plus 2 to the power of 1 times x1 plus 2 to the power of 2 times x2, and so on, right? We kind of know this part. This is from base conversion, okay? Because bit 0 of x is representing how many 1s we have, bit 1 of x is representing how many 2s we have, bit 2 of x is representing how many 4s we have, and so on. So, but we now have the, so if you follow that pattern, okay, if you follow just the usual base conversion method, then we get to 2 to the power of n minus 1 times x n minus 1. This is the most significant bit. This would have been right if we look at x as a unsigned bit pattern. But because this time we specifically say this is a signed value, or x is a signed bit pattern, then we turn this into a negative. That is all. I mean, this really is the difference between signed versus unsigned. In a unsigned representation, everything is added together and we're good to go. In a signed representation, we add everything, but we subtract the most significant bit times the power of 2 corresponding to that bit position. So if we're dealing with an n minus 1, if we're dealing with n bits, okay, n being the width of the bit pattern, then we subtract 2 to the power of negative 1, 2 to the power of n minus 1, sorry. So we subtract 2 to the power of n minus 1 times x n minus 1 from the sum. Okay, this code just craps out. Let me go back and start it again. All right, so I'm back, and let me go back and reshare the screen. Okay. The good thing is OBS does not crash, and YouTube usually does not crash either. So, so that missing portion is still being recorded. But it's rather annoying that Discord would just kind of randomly crash, in the class. I can probably write a script to detect it has crashed out and just automatically restart, but I don't think I have an automated way to restart the screen sharing portion once we get into Discord. All right, so let me get back into the text channel. And we're here. Okay, cool. Magically disappearing trick. Yep, Houdini. Okay, so getting back to signed representation, is this working out okay? All right, so Tom is asking, is it signed or unsigned by default? There is no default. So by default, okay, let me just present it to you. So if I look at a bit pattern of 10110001 in base 2, what is it representing? We don't know, okay? We really have no idea what this is representing. It can be representing an unsigned value. In that case, the unsigned value is going to be 128 plus no 64, but 132, 116, and a 1. Okay, it can be representing this. If we look at this as a signed value, then it will be 32 plus 16 plus 1 minus 128. Okay, so let me just kind of write down what this is. This is the unsigned value. This is the signed value. But guess what? This can also just be representing pixels on the screen. Okay, so if you have one of those really, really old and archaic monochrome monitor, and you send this data, to the monitor, it literally is just saying one pixel that is lit, one pixel that is not lit, the next two are lit, the next three are not lit, and then the last one is lit, or something along that line. Aiden is also correct. If you do not specify numbers, literal constants are defaulted to int, whatever the int type is. Yes. But so there are two questions. Okay, so I really need to clarify those two questions. The way I interpreted Tom's question, which is it signed or unsigned by default, I was interpreting that as inside a computer, when we store a series of bits, okay, or when we look at a series of bits, do we have a default way of looking at the signedness of that particular bit pattern? And the answer is no. Okay, so when we look at 10110001, it really is just literally, okay, that we are storing a 1, then a 0, then a 1, then a 1, then a 0, then a 0, then a 0, then a 1, or the other way around, if you want to come from least significant bit to most significant bit. On the other hand, what Aiden is saying is if you type a literal number, okay, let's say 26, okay, 26, which is a base 10 number. What is the default type in that case is not about signedness. It is about the type of a literal constant in C and C++. So Aiden is correct about that one, that the default is not only that it is signed, it is also of the type int, int, whatever int is for that particular architecture. If you're working on a 32-bit architecture, which by today's standard is kind of old, but we do have those. So if you're working on a 32-bit architecture, then 26 as a base 10 number is basically the 32-bit version of 26 as a bit number, as a base 2 number. On the other hand, if you're on a modern 64-bit architecture, then 26 as a base 10 number is internally known as a 64-bit representation of the value of 26. So is that clear? Is everybody understanding what I am trying to differentiate? One is about the internal representation. Does the processor has a default way of looking at a bit pattern? The answer is no. The other one is a programming language question, which is when we type a literal value as a number, does it have a default type? And if so, what is it? The answer is it is by default just int, which is signed in C and C++. All right, so I'm hoping I'm making that clear, because it really is important to make that differentiation. As the class goes on, the separation between what is inside the processor and what you know from programming in C and C++ in CISP310, that difference will be even more obvious as we continue with this class. All right, so we are out of time, but I do want to give you one example of how to apply this particular observation here. But before that, let me answer Tom's question. So it depends on where you are applying it. Can you be specific about what it is referring to? Signed versus unsigned inside the processor? I think this goes back to the earlier question that we have of, most of the time we don't care about whether something is signed or not. The only time it matters is when we compare. Exactly. What do we care? Yep, exactly. So inside the processor, unless an operation is trying to determine whether a value is less than another value, we don't care whether it is signed or not, because all operations are the same whether it is signed or not. But in C and C++, everything has a type. So that's why when we specify a bit pattern in C and C++, there's always a type, which also means there's always a signedness associated with the bit pattern. That's in a C program, C and C++ program. On the other hand, when we're looking inside a processor, when we look at the transistors, then there is no such thing, okay, until we have to perform comparison operations, which is the next module. Okay, so let's go back to this question here, okay, and apply, apply this particular bit pattern to this definition over here. So we're going to look at 10110001 in base 2. So if we want to look at this as a signed interpretation, then we are basically looking at a 1, okay, 1 times 1 plus 0 times 2, because bit 1 is a 0, and then a 0, oops, I made a mistake here, there we go, and a 0 plus 4, because bit 2 is also a 0, bit 3 is also a 0, so we don't have any 8s, okay. So this part is really boring because we should have mastered this already. There's 116 because this particular bit 4 is a 1, and then we have a 32, and then we move on to the bit corresponding to 64. There's none of those, okay. But now when we move on to the most significant bit, there is a 1 over here, but instead of adding 128, which is the next power of 2, we are subtracting it. But you can also see that we can also say we're adding, but this time we're adding the arithmetic negation of 1 times 128. So it doesn't matter how you look at this, you can say this is 1 times negative 128, same thing, okay. The bottom line is the most significant bit is no longer representing how many 128 we have. It is now representing how many negative 128 we have, and that is because we choose to look at 1011 0001 as a signed 8-bit number. Yes, we did, Tom. It is up here somewhere. Okay, I'm just gonna quote Daniel. There we go. So I think we're done with today's lecture. We haven't really talked about comparison yet, so I don't want to give you the next lab. If I gave you the next lab, you guys actually would be able to do it, and learn about comparison, at the same time. But I don't want to kind of do it that way, so we do not have a lab for tonight. So instead of celebrating and say that woohoo, we don't have any lab tonight, you might I know most of you are already thinking, yep, we are just, yeah, exactly, Christian is already right. But I think it is also important to point out that we are moving on to binary number comparison as our next module. So I would spend the time to review what we have talked about today, which is signed value representation, 2's complement, and stuff like that, and also move on to binary number comparison. Binary number comparison is really kind of interesting because just like with addition and subtraction, we are trying to bridge the high-level concept of comparison to the low-level concept of how do we look at individual bits and use AND or not, exclusive OR, to perform the comparison. How do we know a value represented by these bits is less than the value represented by those bits? Okay, so it's basically a bridging type of explanation for this particular module. And certain parts of it can be very confusing, okay, because there's a sign bit. Okay, let me just kind of quickly explain what bits we are talking about. We're talking about the borrow bit, which we say, yeah, we got that, okay, we have mastered, the concept of borrowing. Great, okay, that's good. There's the sign bit, which we talked about today. The sign bit is nothing more than the most significant bit of a bit pattern. We go like, okay, that's really easy, no problem. And then after that, we have the overflow bit, okay? So the overflow bit is starting to get a little bit interesting, okay? Because it has to do with whether the sign of the result of a subtraction makes sense or not, okay? So when you get to that portion, you'll know what I'm talking about. And then last, okay, we have an L bit, okay? The L bit is defined by some of the other bits that I have just mentioned, so that when the L bit is 1, it means the minuend is less than the subtrahend in the subtraction. So by no means is binary number comparison a easy, light module. It is, in fact, I would say it's a little bit harder than what we have just gone through today. So I would advise everybody to read ahead of me, okay? At least get some exposure to those concepts and names ahead of time, so that when we get to binary number comparison, we wouldn't be as confused. And also, the lab of subtraction and compare will open on Thursday. So having a thorough understanding of the concepts will only help to get you through the next lab quickly. All right, enough time to watch Arrival and The Matrix too. If you watch 2 movies at the same time side by side. Just watch one using the closed captioning and then listen to the other one. It will work. All right, so I think we're done with today's lecture. Okay, so I think we're done with today's lecture. There's no lab for today, so we only got 2 things to do. One is make sure that you are done with the role taking activity, which looks like most of you are done with that already. And 2 is to review today's stuff and read ahead of me for Thursday. So I'll see you guys on Thursday. Well, more like you'll see me on Thursday. Yep, I'm gonna have a good meal. Yep, I'm just like what Christian has quoted, so I'm gonna put that again here. All right, I'm going to turn off the voice channel